Hello, welcome. I'm having this talk about real programming. The theme is from the book that my friend Nils and I wrote. Mostly Nils wrote the book about various projects he did, optimization. I met Nils at work. We met immediately over some real pressing programming issues. We had this image pipeline that was very time constrained, and we needed to hand assemble some routines to make this thing go faster. And my background is in graphics, so I have worked with a lot of graphics packages, Lightwave from the Amiga, Deluxe Paint, and when you work with graphics you usually have a lot of data, so it's always a constraint on the amount of power that you have. So I'm going to talk about these things, how we deal with the need for real programming, and how we implement that, why we implement that. Okay. So back in the days in the Amiga, can we have the hands up, the Amiga people? Let me hear it for the Amiga. All right. Yeah, this computer was like a 16 megahertz wonder machine. It was the first multimedia computer that actually showed music and did photography in a realistic manner at a good price. So we worked this computer really hard to make it push through. So we learned to work with graphics on a low level. And this is what Nils and me took with us from the age of the Amiga and up to today. We are used to working with copying graphics line by line, by making interfaces the old-fashioned way, by blitting parts of images to other parts of images. Those are just memory transfers. So when we today work with much higher resolution images, we have the same constraints. We run out of power all the time, and that's why we press the need for efficient programs. So we have this popular book which goes through a lot of techniques for dealing with graphics. The graphics that you see here are rendering in real time through an engine that I wrote. It's about 3,000 lines. It's very, very compact and reasonably performant. Those are 3D objects. We are dealing with the same kind of primitives that we always are dealing with. We have bitmaps and we have 3D graphics. Basically two kinds of graphics. I don't know many other types of graphics. When dealing with 3D graphics, you need it to go fast. As with bitmap, you need it to go fast. So you need someone to optimize this. Now, the trend today is to say that we don't need this speed because we have so much power in the computers. But on the Amiga, we had 50 frames per second, and that was 7 megahertz. And today, I experience a lot of laggy applications, things that just doesn't move. You'd expect it to work fast because you are on multi-gigahertz processors. So where does all the power go? Are we just heating up the planet? What are we doing with those gigahertz? How is it possible to wait for very simple operations on a modern day computer? So what I am saying is quite contrary to the popular belief that today we have object orientation, we have modern techniques, we have many new languages, they are popping up every week, but we go back to basics. We program almost exclusively in C, and my experience with graphics packages is that they are all made in C. There are no other graphics packages out there. When you're dealing with the video editors and also music software, it's mostly just C, some C++, but as you'll hear, we do not like those abstractions. We don't feel that the abstractions that are there to simplify the handling of subject matters actually simplify, because the promises that we've had is that when we are using modern paradigms, we are taking away some of we are dealing with complexity, but what we are really doing is we are hiding complexity. Complexity is still there, and it's hidden. So whenever there's a problem with a C++ program, it's hidden. So we like to deal with C because it's very straightforward. It's very predictable. You know what it's doing. It's easy to debug, and it's perfectly fit for the type of programming that we do, which is image pipelines and the high performance data processing. So in the book, you'll find that there are many chapters on scaling and filtering of images, but there is also a chapter on optimized encryption. We have chapters on parallelization, and what you'll discover is that in C it's possible to do all those things that you now have modern constructs for in all the languages, to parallelize, to make some kind of a synchronization between the threads. You can do all that with very simple means in C. The same thing goes for many of the containers like vectors and linked lists. It's mainly just a pointer and a size. It's a next pointer, and they are very simple constructs, and you can make one in a few lines of code. And this is regularly what we do. We make complex behaviors in few lines of code. And there seems to be a misconception that you can actually measure a program's quality by its weight, which is totally opposite of what is really happening. So all things equal, smaller is better, simpler is better, fewer dependencies are better. And here you can see the basic rules that we try to operate by. We program mainly in C, GLSL, and assembly. So assembly optimization is very useful when you have constraints. And in the world of imaging, you run into different chips, but the problem is usually the same. So you'll have different instruction sets, but you have to push the images through. So the width of the registers and the number of registers kind of dictate how much images you can put through per second. So if you're going to do 8K at 60 FPS, as is soon going to be the norm, you're going to need very, very fast image pipelines. And for this, assembly is one way to do it. Hardware acceleration is one way to do it. And when you're talking with hardware acceleration, for example, I have been dealing with the NVIDIA encoder, and you download the dev kit for the video SDK, and you'll discover there is a huge thing. It's about 10 megabytes, and there's a huge example that tells you how to use this. It depends on CUDA for the color space conversion. All this we can throw away, because the thing that you actually need is just the header file, and it links directly to the driver in the system. So it's a very simple thing, and there is actually a document of 1 page that explains the whole encoder, how to use it, and you can interact directly with the encoder in C, and it's much, much simpler. So look beneath is the last point on the list, because beneath every object-oriented system, there is usually a simpler, faster, better C system on which is it built. This is also true for example, the Oculus system, also coming in with examples in object-oriented C++. But underneath, there is actually a very functional C interface, which is much easier to handle. Also, the abstractions on top tend to take away opportunities that you actually have. So in the end, you'll end up having to access the lower levels. So if you just start at the lower levels, you'll avoid a lot of problems dealing with complexity, which is what we are trying to avoid. So I mentioned this program here is about 3,000 lines. We have shaders here. You can see the optimizations of the shaders in the book. And it's very interesting because we are doing graphics, and Nils, he loves to do fancy graphics, and to calculate those graphics, there are many calculations. So this is what the graphic cards are doing. But there is nothing that says you cannot insert any kind of data into that shader and process it either by GLSL and pretend that it's textures. But you could put seismic data, you could put anything in there and pretend that it's textures, and you'll be working with very fast hardware, and it's quite convenient to work with. And you can bootstrap this from C simply and make very effective pipelines with very few dependencies. So we tend to make our pipelines ourselves because there are many systems out there. You have OpenCV, Halide, plenty of systems for dealing with images and graphics, but usually they aren't all that fast. They introduce huge amounts of stuff. They're big, expensive, and ugly, and this...
We don't want this. Look at it, it's overkill. It's expensive, it's big, and it's ugly. It's gonna have to get a hell of a lot worse for us to even consider.
Yeah, so that's the moose from the movie Chappie. It's a really hilarious scene where he's offering missiles to handle urban crime, and it's kind of like the RoboCop monster, like Ed 209. And let's...
We don't want this. Look at it, it's overkill.
I'd like to say some more. Okay, so responsiveness means a lot to us.
The whole thing's coming with this. We don't want this.
Let's see if we can jump back.
It's expensive, it's big,
yeah.
And it's ugly.
Okay, so keep it short and sweet. Always in our mind, you need to take away anything that's not doing the thing. And we always optimize for smaller, less dependent, less complex, very simple. We don't deal with like environments, we deal directly with functions and data. And we try to keep it as direct and as simple as possible. And we'll go to great length and spend a lot of work simplifying things that came in a box, ready to use. Because we know that this box is filled with crap that we don't want. And that this thing is eventually going to bog down our project and make the whole thing unmaintainable. So we prefer to find out how things work, remove anything that isn't the thing that you want, and all problems can be reduced. We reduce all problems to the absolute minimum of what the solution is, and that solution we take with us. Now we have a box of many small solutions that we handcrafted, and in C you can link this together very simply. It's very simple to link things together in C. You can make plugin systems, you can do DLL exports and things like that. All the graphics packages, they work like that. They have a C engine that runs the graphics, and if you want to make shaders like the fur shaders in the cartoons, you need special programs that draw the fur. We could make it here in GLSL and have real-time fur. You'll see it in games, and you can make it as a plugin. So it's a very simple interface, and those interfaces we like. Don't care much for those patterns. So let's jump to the things that we don't care much about. Best practices. Most of the time we are being told that there are many rules of things you can do. Don't use this, do that, and it's become like a very single-minded focus on things that probably have great value in huge corporations, which we are not. We are individual programmers that strive for efficiency, and I do not care so much about all the rest of the world and how they might find my code, because I will wrap it in a simple interface and it will run as a simple unit and it will not interfere with everything else. And that's what we try to avoid, the kind of unnecessary constructs and especially bindings between libraries, because it seems that in every large project you have so many languages, you have so many parts, so many dependencies, that eventually they all crumble under their own weight and become low quality software. And as we mentioned here earlier,
we don't want it. I mean, look at it, it's overkill. It's expensive, it's big, and it's ugly. It's gonna have to get a hell of a lot worse.
If you just use average standard techniques, you'll probably end up with average standard software. The problem with average standard software is the same as with the average startup company. It doesn't succeed because only the top software will survive. You'll not have a lot of successful average software packages. You'll see that the ones that float to the top are the ones that are optimized. And we've seen packages come and go, but some things stay the same. For example, when you're dealing with 3D graphics, you're dealing with points, vertices, matrices, and this has been the same for as long as I have been doing 3D graphics. 2D graphics is the same. It's the same problem all over again. So all those new solutions usually don't solve much new, except for the graphics cards that are really giving us a lot of power. And we need to harness this power, and we do not harness this power by thinking that we have too much power and we can do whatever we like with it, because you will run out of power, which is why when I press the button in my Android car, it takes 2 seconds for the requester to come up and let me type text. I have no idea how a 2 gigahertz computer can do that, but it does take 2 seconds. And that's because things get implemented with toy languages. We have a chapter about that. And toy languages are languages that can never perform. You can probably make simple programs, but it will never scale. Of course, you have like the big companies that implement huge parts of their pipelines in what we call toy languages. So for some problems this would work, but we are in imaging and high performance computing, and we do not need the extra weight of languages that do not work efficiently on any processor. And in addition, when you are working with other languages than C, you'll have bindings, and now you need to maintain the bindings. And what we regularly see with all kinds of languages, except for C, is that the versions keep changing, the language keeps changing, and they are no longer compatible. So we like to play around, and this is a quote from the book about a video player that Nils made on the Amiga. He made this MPEG player, but unfortunately he had encrypted all the files. And that's why the player needed brain surgery to decrypt the files. So he had to go into the 20-year-old assembly language and decrypt the video before we could reconstruct it. So we did some reconstruction of all the videos, and we took some VHSs, upscaled, and put it on YouTube, and salvaged some of the older projects that we made in our youth. And that was a lot of fun. And it's also a practice for how you can deal with images. And the descriptions that Nils put in the book are very descriptive about how his thought process is working when he's optimizing and dealing with images, because these are hard problems, and when you run out of power, you're out of power. So what do? Well, you could send it to the cloud. All right, and now you'll be paying per second, running in a language that can never perform, in a computer far away. And this is going to be very expensive. So when we measure the cost of development, it's often said that it's very hard and very difficult to develop quality software in C because of the very rudimentary nature of it. But the fact is, it's not hard at all. It's very simple if you just deal with data in the simple, direct manner that data should be dealt with. If you deal with 3D objects as points and textures, this is very well-known subject matter, and it's solved basically the same every time. Every 3D program does the same thing. This is a ray tracer. It's running in 60 FPS, real time, tracing a lot of rays here. So that's a physical simulation running in real time. We do not have to upload this in the sky. We do not have to wait until Tuesday to know the result of the tracing. We can make a perfect simulation of rays. Very simple, because it's very simple mathematics. And you can use this for optics. Basically, those are mirrors. You could use them with lenses and refraction. Becomes very fast, very expensive. You're going to need the power. And that's what GLSL, C, and Assembler delivers. And that's why you use this exclusively. And we do not ball around with lesser languages, because it's counterproductive. You need pipelines that perform. You need software that has quality. You need things that are responsive. And especially for this new future of robotics and imaging, scanning, like we have cameras in this room. We have some information about the space that we are sitting in. So how do we deal with this information? How can we count the number of heads? It's known. We can do it. We could not do that in real time, or could we? If we write efficient implementations, we can do a lot of work in real time. And we're going to have to do that if we want self-driving cars, autonomous robots, all kinds of nice things that the future offers. We need to build efficient machines to do this. We do not have any power to waste, and we need to learn how to optimize. And that's why it's really fun that Nils wrote such a good book, and that I could make some graphics and take part in that project. Because in the end, we're going to need people who know how to optimize. And I waited a long time to find a guy like Nils that sees everything like I do. He understands the constraints. He understands the need to fight those constraints on every level so that you can write fast, responsive software that scales. Because when your routine is quick, it can handle a lot of data. So you could make a face recognizer, but could you make an all-face recognizer? How about we put in more people? How about we also do chairs, geometry? How do we map the room so that we could introduce robots that actually can interact with us and do useful work? We're a long way from that. And the only way we can get there is by writing very, very efficient routines. And the hardware gets there. The hardware will get there pretty soon. But the software seems to be lagging behind. So that's why we would like to present to you all the book and hope that you all will see with us.
The city's tearing us apart. The whole thing, the city's tearing us
That-
apart. The whole thing's going tits up. All right, we have to take.
That we have to take control. Have to take control of the machines. We have to write performance software that actually works, that actually does a lot of hard work in very short time, so that we can make the perfect machines for a better future for all of us. Thank you very much. I hope you enjoyed the talk. And here are the credits, here are the greetings. I have used for this 3D system the CGLTF library. That's the GL transfer format. It's an object format. VMAT library, very, very simple library, not object-oriented. Font generator, 3D modeling with Blender, and tracked music with the Milky tracker. And I'm planning to build a soft synth into that tracker so that we can have real soft synth sound. Okay, thank you very much. Any questions? Any comments? Yes?
I mean, you have to balance it all off. But sometimes you said, okay, it's okay that something is slow, and you're using not the fastest, because, well, you said performance doesn't matter, but sometimes performance does matter.
Well,
I can give you an example.
yeah, thank you.
Let's say we want to, I'm working with a lot of RF, something called a spectrum analyzer,
Yeah.
and that can run for, let's say, an hour. So the command we want to run to command this spectrum analyzer
Yeah.
doesn't have to be fast. However, if we want to do the job ourselves, and we want to have an analog digital converter and run, for instance, faster and transform,
Yeah.
then you need fast software.
Yeah, I actually did implement a fast Sjur transform. Actually, I found it on the net, and I run it on my old computer. It was a Pentium 90, and it does music in real time. So you can do that very easily. If you increase the frequency, you can do it very accurately, and you can actually do the whole thing as an image. Then you can do image transforms. Like, for example, you can brush out parts of the music that you don't like. Then you can do the inverse Fourier transform, and you'll have back the music without the parts that you didn't like. So you can treat the thing as an image. So, first of all, fast Fourier transform can be very, very fast. I don't see any reason to make it slow.
So, what I'm saying is sometimes
Yeah.
toy languages and whatever you call it could be useful because it does something simple.
Yeah, but it's very simple to do that in C. I did it. It was about 40 lines of code in C. It's a very, very simple thing, and it runs very fast in C. And then you can do things with it, and you can include it in your next project and your next project, because that code will not go out of version with your library, unlike most of the languages that we don't use that tend to not work after a few years. In fact, that program that I made, it still runs like 15 years later on Linux in Wine, because quality software has a tendency of keeping working too. You remove the dependencies and it will still work in many years. And you can reuse the code by pasting it or copying it into your new project. So there are many reasons to use whatever you have at hand and you can understand, but you can always do it better with C. And that's why I wouldn't waste time learning to do this in a language that can never scale to the level that C does. And because it's so simple, I mean, I couldn't do it in JavaScript. I couldn't. I don't know the language. But it's very simple in C, so why would I learn JavaScript to do something that is very simple to do faster?
There are things I would do in JavaScript, and there are things that I never ever would do in JavaScript.
Yeah, probably, and that's part of the reason why we have this talk, because I am very contrary to everyone, and it has to do with my background. It's a thing that I've seen over time, that people tend to choose the simpler solutions, and then they get locked in with the simpler solutions, and we just don't have anyone who can actually do the work of optimizing the pipelines for the kind of robotic vision that we need. We just don't have the people, because everyone learned to do this the slow way, and now you have a lot of tractor drivers and no space pilots. Okay, thank you.